When you've completed this lesson, you'll be able to recognize parallel and perpendicular lines and understand their properties. You'll also be able to measure angles and find unknown angle measures in triangles algebraically. Photonics technicians use geometry often involving parallel and perpendicular lines. Photonics technicians also measure angles between lines and beams that are not parallel. When angles can't be measured, the properties of the triangles can often be used to deduce the angles. For example, we have Brewster's angle of reflection for producing polarized light. Or we have Snell's law of refraction for tracing rays passing through an interface of different media. All of those will involve determining and measuring angles. Let's look at an example scenario. Laser cavities use Brewster's windows to achieve polarization of a laser beam. The drawing shows an unpolarized incident ray striking a window, undergoing reflection and refraction, and exiting partially polarized. So we're asked to find angle A1 if it's to be Brewster's angle A2 for the reflected ray, angle B1 and B2 and B3, and angle B4. All right, so that's a lot of angles and lots of geometry and lots of calculations, but we'll be able to do this once we go over some of the skills necessary to complete this problem. So let's return to this a little bit later. First, let's review some of the terms and definitions pertaining to lines. Parallel lines are two or more lines that never intersect on the plane. These line segments are all parallel. Perpendicular lines meet at a 90-degree angle, and we say that they form a right angle. That's the term that you often hear, or that they're square angles. Notice that the symbol used looks like a little square. If you have two of them back to back, it looks like a little step. A ray is a line segment that has an arrow on it, meaning that it keeps on going forever and ever, and it has an endpoint. And that endpoint is useful because if you have another ray starting at that same endpoint, you form an angle. And we want to be able to measure those angles. We measure angles using degrees. There's 360 degrees in a circle. And just like there's 60 minutes in a clock hour, well then each of those minutes must have 6 degrees in it, just to give you an idea of how big a degree is. We will refer to special groups or classes of angles. For example, the acute angle is greater than 0 but less than 90 degrees. A right angle, as you've already heard, equals 90 degrees. And an obtuse angle is greater than 90 degrees but less than 180. And of course, you know what 180 degrees is. That's just a straight angle. Let's look at example 1 of measuring angles. How would you measure angles? So we're going to measure an angle with a protractor. So let me show you how to use a protractor. You align the midpoint mark of the protractor with the vertex of the angle, right there. Now your protractor might have some more plastic down at the bottom part of it there, but I've just drawn this one here without that so that it makes it easier to line up. You'll align the midpoint mark of the protractor with the vertex of the angle, of the endpoint where the two rays join together. You align AB with the 0-degree line of the protractor, so be real careful to get both the point on the 0 and the end point on the center of the protractor lined up perfectly. And then you'll be able to read the measure of the angle up here on the protractor. Protractors will often have double sets of numbers, and so you'll have to realize that we're starting off at 0 degrees, going 10, 20, 30, 40, 50, 60 to get up to here. So don't let the other numbers confuse you. That would be for measuring an angle that started from all the way over on the left-hand side, and that would be 120 if it came all the way over here. So in that case, angle CAB is equal to 60 degrees. And you'll notice that we refer to the angle by those endpoints that are used to construct the angles. Here's one where we'll draw an angle using a protractor. So we're given ray IJ, and we're asked to draw an angle JIK. So we need to find a point K out here that will produce a 120-degree angle. So again, we'll align the midpoint just like we did before, and line up the line right on the 0 degrees line here. So now if we wanted to draw a 10 degrees angle, we'd have a line coming off here, or a 60-degree angle, the line would come up this way. What we need is a 120-degree angle. So we need to come all the way over to 120 degrees and put the dot right there and label it point K. Now we're ready to draw a straight line that joins I to K, and you can use the edge of your protractor to do that. And there you've got it, angle JIK, 120 degrees. Triangles are going to be very helpful in geometry in ascertaining different angles, because we know that a triangle has 3 sides, and we know that it has 3 vertices, and here we'll label them A, B, and C, and that there's 3 angles inside of that. And there's 3 angles inside that triangle, angle A, angle B, and angle C, and you'll see how they correspond to those vertices. In every triangle, the sum of the measures of the angles always equals 180 degrees. That's a very important fact for you to remember. The sum of the angles in a triangle always equal 180 degrees. So let's look at example 3 that asks us to solve for the angle in triangle A, B, and C if we know that angle A is 105 degrees and angle C is 48 degrees. So how can we find the measure of angle B? So we know that the sum of those angles must equal 180 degrees. That's what we just learned above. And so we'll say 105 degrees plus angle B, whatever that is, plus 48 degrees has to all equal 180 degrees. So all we have to do now is the algebra to solve for angle B, which you know means that we take 180 degrees minus 48 minus 105 equals 27 degrees. Now, there's some important terminology that you may encounter in your studies with triangles. For example, we have equilateral triangles that have 3 congruent sides. We show congruence many times with just putting a tick mark on the equal sides. We have isosceles triangles, which have 2 congruent sides. And we have scalene triangles that have no congruent sides. Every side is a different length. The measures of the angles of the triangle, there's another way of describing triangles. There's equiangular triangles, which have 3 congruent angles. We have right triangle that has a 90-degree angle in it. Those are very common and very useful. We have acute triangles, where all the angles in the triangle are less than 90 degrees. And we have obtuse triangles, where one of the angles is greater than 90. Now, those terms aren't really so important that you can't exist without them, but if someone mentions to them that you have an acute triangle, now you'll know what it is. Example 4 asks us to build a toolbox using some geometry. So we have a toolbox here with a rectangular compartment in the middle of it, probably to put some smaller tools or something, and we have a divider going across the diagonal B and D. And we're asked what will be the measure of angle X and of angle Y. And you'll notice that we're given one angle of 35 degrees. And how are angle X and angle Y related? Well, first of all, the corners of a rectangle always form 90 degrees. And so you'll see here that we have 2 right triangles here. The sum of the angles in each of these triangles equals, as you know, 180 degrees. So in triangle B, C, and D, we'll have 35 degrees plus the 90 degrees plus X equals 180. just like we saw in the previous example. So we can solve for x, and we'll find that x equals 55 degrees. So the diagonal makes an angle of 55 degrees with side BC, the short side. So now we're trying to find angle y, okay? So since angle CDA in this corner equals 90, correct? Is that a right angle? If it's a rectangle, all of the corners right here equal right angles here. So we know that 35 plus y is equal to 90 degrees, and we can solve for y and find that y equals 55 degrees. And what is the relationship between angle x and angle y? Well, look at that. They both turned out to be 55 degrees. So there's something that you learn about diagonals in a rectangle. What do you think about angle z? Would you like to venture a guess? I bet you'll already know the answer without even having to do any math. It's going to be the same as this angle over here, so it'll be 35 degrees. Very good, so you're learning very fast. Now we're ready, I think, just with all that, to go ahead and look at our opening scenario. So we're asked to find our angle A1 if it's going to be a Brewster's angle such that the tangent of B1 equals n, the index of refraction in our glass. So we have n is equal to 1.5 in our glass, and we have angle A1 coming in over here, and it's going to reflect and refract. For angle A1 to be a Brewster's angle and the tangent of A1, it's going to have to equal n, 1.5. Now, you may not have encountered the tangent function before, but we'll go ahead and look at that at the next module, but you can still use it in your calculator. The tangent of A1 is equal to 1.5, so if we take the inverse tangent of both sides, that'll give us A1. The inverse function of the tangent function will give us A1. So if we take the tangent inverse of both sides, and we have the tangent inverse of 1.5 is equal to A1 if you use your inverse tangent function, or your 10 to the minus 1 power that it looks like on your keys, and you get 56.3 degrees. A little caution here, be sure to put your calculator in degrees mode. Some advanced calculators can be in radians or degrees, and you'll need to make sure that you're in degrees mode. And one way to find out is that if you don't get 56.3 degrees for doing this problem, then you're probably in radians mode. All right, so part B of this problem says, what is this angle A2 for the refracted ray? If A1 comes in at the Brewster's angle, what is going to be the angle for A2? So in general, the angle of reflection measured with the normal always equals the angle of incidence measured with the normal. So this is the normal. This is the imaginary line that we draw that's perpendicular to the surface of the media. Perpendicular means what? It means 90 degrees. So if angle A1 comes in and angle A2 is the angle of reflection, and those are equal, then it's pretty obvious that A2 is equal to Brewster's angle, which we just calculated in part A in this problem, 56.3 degrees. Part C says to find the angle of refraction. The angle of refraction is also measured against the normal. And so we've got angle A1 coming in and angle B1 coming out of the interface of the media, measured against that normal line. So we'll substitute in our variables into Snell's law, which says that n1 sine theta equals n2 sine theta 2. So here in our case, we have n1 is the index of refraction of the media outside, which we'll presume is the air, and the index of refraction of 1, and n2 is the index of refraction of the media that we're going into, which will be 1.5, and angle A1 will be the angle of incidence in the air, and angle B1 is the angle of refraction inside the media, and in this case, our glass. So we need to isolate our term there with the B1 in it. So since it's multiplied by n2, we need to divide both sides by n2. And the sine of b1 will equal n1 sine of a1 divided by n2, and then we can go ahead and plug those variables in and calculate. We'll take the inverse sine of both sides. Since we don't want the sine of b1, we want b1, just like we took the inverse tangent. Well, we'll take the inverse sine, and the inverse sine of 0.5546 is about 33.7 degrees. So the ray is refracted inside the glass at about 34 degrees from the normal. Next part asks us to find the angle B2 and B3. B2 and B3 are the angles of incidence on that second interface, and B3 is the angle of reflection from that. And we'll notice that both of those are referenced to new surface normal there that we're looking at, not the old one, but this new one. Look at B2, and you'll notice that B2 is part of a right angle formed by the angle of the normal in the glass surface. B2 is part of that angle, and the other part of that angle is angle QRP. Well, QRP just happens to be part of a triangle formed by Q and QRP, and we've seen that triangle, and it has angle B1 in there that we just measured. We just determined B1 to be 33.7 degrees. So now, if this is a right triangle, and we know that B1, and we know that this is 90 degrees, then we can calculate the third angle, QRP, which is 180 minus 90 minus 33.7 equals 56.3 degrees. So angle QRP is 56.3 degrees. All right, so now that we know angle QRP, we should be able to calculate B2. So B2 is equal to 90 minus QRP, or in this case, 33.7 degrees. As before, we can quickly identify the angles of B3 because this is a reflection, just like we saw up here. So we'll have a reflection down here, and we've learned that the angle of reflection equals the angle of incidence. So in this case, B3 equals B2, which is also equal to 33.7 degrees. And thus we can know, interestingly enough, that B3 equals B2 equals B1 equals 33.7 degrees. So all of our labeled angles inside there equal 33.7 degrees. Find the angle, finally, of refraction for B4, the outside, when the ray leaves the glass. What angle does it make with that normal? To do that, we'll once again use Snell's law, which defines what happens between the interface between two different media with two different indices of refraction. In this case, N1 will be the glass, which will be 1.5, and N2 will be the air, which we said is 1.0. And the first angle will be the angle of incidence at the interface, which will be B2. And the exit angle will be angle theta 2, or B4. And of course, we want to solve for B4. So here's Snell's law with our variables plugged in. We need to isolate the term with B4. Since it's multiplied by N2, we'll again divide both sides by N2, which will leave sine of B4 on the left side and N1 sine of B2 divided by N sub of 2 on the right side. And we can substitute in our values for N1 and N2 and our angle for B2, and we'll determine that our sine of B4 will equal 0.8323. If we take the sine inverse of both sides, then B4 will equal the sine inverse of 0.8323. Again, using your calculator of the inverse sine function, so you can find that B4 is equal to, oh, there's a number that we've seen before, 56.3 degrees. And it's exactly the same as Brewster's angle. Isn't that interesting? So the angle of incidence on the ray over on this side is the same as the ray exits on this side. It's just been shifted down a little bit by the refraction of the curves inside the window. All right, so now it's time to look at some practice exercises for this module that'll build up your confidence so that you can actually do these types of geometry problems. So first of all, let's answer these questions about this drawing here. If angle 1 is equal to 90 degrees, what can you say about these two lines L and M? Well, the lines meet at 90 degrees, so lines L and M are perpendicular. And we use sometimes this symbol here to indicate that L is perpendicular to M. So if P is perpendicular to L, what would be the measure of angle 2? Well, again, we'll apply the definition of perpendicularity. That means angle 2 must be 90 degrees if P is perpendicular to L. And if angle 1 is 90, then what is the measure of angle 3? Do you remember that terminology that we had about straight angles? Well, that's a straight angle right there, and we know that that must be 180 degrees. And so 1 plus 3 must equal 180, and we can solve for 3 since we know what angle 1 is, and that'll make it 90 degrees. If angle 1 were 90 degrees, what can we say about the measure of angle 4? There's a couple ways to answer this. One of them is that if we know that angle 1, 3, and 4 form a straight angle with line M, making a straight angle with 90 degrees, well then angle 3 and 4 must also form a straight angle. So we can say that angle 4 must be 180 degrees minus angle 3. So angle 4 must be 90 degrees. So an interesting fact not covered in the text is that when you have two rays crossing each other like this, these opposite angles are always equal. So angle 1 and angle 4 are always equal. And angle 3 and this angle that's not labeled over here. And there is one more part to this. What can you say about lines M and P? These two distant lines here. Both lines M and P are both perpendicular to the same line, and that just happens to make lines M and P parallel. And there again is the symbol that you'll see that M is parallel to P. So here's exercise 2, a little bit more real world kind of problem. See if you can complete the statements about the sketch here. The drive shaft is blank to the rear axle. So what does that mean? What is the relationship between the drive shaft and the rear axle here, shown in the drawing? Well, it's perpendicular, right? All right, so that was easy. So how about the rear axle and the front axle? How are they compared to each other? So you've probably figured it out by now. They're parallel. Very good. So this one's a little bit harder. The drive shaft is what to the direction of travel? Well, it's also parallel. And here's one that we did not cover in the text. When the tires of the car have spun around 360 degrees, that's 1 revolution, the distance they have moved on the ground is about the same as their circumference. So that's simply the definition of the circumference, the distance all the way around the circle. So, of course, as a tire rolls on the ground, it'll actually trace out the circumference of the circle onto the ground. Exercise 3 asks you to solve for x in some triangles where we've given you a couple of angles. So we know the sum of the angles in the triangle equals 180 degrees. So this should be pretty straightforward. You've seen this in this unit. So x plus 114 plus 39 degrees equals 180 degrees. So you solve for x and subtract 114 and 39 from both sides, leaving x as equals 27. And what kind of triangle is that? Is that an obtuse triangle or an acute triangle or what? Right, it's an obtuse triangle because it has one angle that's greater than 90 degrees in it. Now, note the straight angle in this triangle so that you can identify that the missing angle here must be 60 degrees, right? So 180 minus 120 equals 60 degrees. So now you can solve for x, just like you did before. X plus 60 plus 67 must equal 180, and x is equal to then 53 degrees. And that concludes our treatment for Module 8, Geometry. I know that you're going to have a lot of fun working with angles and perpendicular lines and triangles, and it's a fun thing to do, and you'll encounter a lot of geometry in your photonics career. So study up and learn this stuff very well, and I'll see you next time.